Okay, today we're going to do 1.3 equations and graphs of polynomial functions. So if you haven't done your minds on for 1.3 already, go ahead and do it. So by the end of today's lesson, you should be able to determine both algebraically and graphically if polynomial functions are odd or even functions. That's not the same as odd or even degree functions. You're going to be able to determine intervals where the polynomial is positive or negative, and you're going to be able to determine possible equations of polynomial functions given a graph. You're also going to be able to sketch a nice graph of a polynomial function. Okay, let's go. There's the answer to the minds on. So the least possible degree, that comes from the number of zeros, 1, 2, 3, 4. So we know the least possible degree is 4. But we know that this can't possibly be a degree 4 polynomial because it extends from quadrant 3 to quadrant 1. That means it's odd, so we would have to bump it up to the next least possible degree, which is 5. We could also just double check our turning points. 1, 2, 3, 4 turning points, which means our least possible degree would be 1 more than that. Let's see, the sign of the leading coefficient, we already talked about that. It goes from quadrant 3 to quadrant 1. So of course that's a positive odd degree function. And so positive leading coefficient, quadrant 3 to quadrant 1. And point symmetry, there is no point symmetry because there's no point where we can kind of take it and act as the pivot and turn this graph 180 degrees and get our original graph back. I drew a little thing in here because if this was this long here, if this sort of peak matched this valley, then there would be a point symmetry right here. As you can see, you could rotate it that way and you could get this graph. But that is not the case, and so we would say no point symmetry. We don't have to consider line symmetry. This is not an even degree function, and so we're only saying there's no point symmetry. Okay, let's start the lesson. So, I have a lot of information to disseminate here. Don't panic if you're not following quite yet. We'll do some examples, and hopefully it'll come at that point. Okay, so the graph of a polynomial function can be sketched, and we will be sketching them using the x-intercepts, or the zeros, the degree of the function, and the sign of the leading coefficient. All right, when a polynomial function is in factored form, and you know what factored form is, that's when there's usually brackets, the zeros can be easily determined from the factors. Of course, you know that from grade 10 and 11. When a factor is repeated n times, so when it's repeated a number of times, of course you would see something like this. If it was repeated 3 times, there would be a cubed on it, for instance. So the corresponding zero is said to have order n. That's kind of like degree of a factor, okay? But we call it order. So the degree of this factor is 3. But we call it an order 3 factor or an order 3 zero, because the zero of this is x equals negative 3, and the zero then would have an order 3. Let's look at this example. It says the function f of x equals x minus 1 squared times x minus 3. This has zeros at x equals 1 and x equals negative 3. This exponent on this factor is 2, so this is an order 2 zero. And this one has an exponent of 1. This is an order 1, 0. The whole function has a degree of 3 because we add up the 2 exponents. Okay. The graph of a polynomial function changes sign. So it goes from being negative to positive or positive to negative only at zeros of odd order. So if we are at a 0 of even order, the function does not change sign. And if we talk about zeros of odd order, like this one or this one, we can see that there are certain characteristics. And I'm just going to go to Desmos And what we're going to do now is we're going to explore it very quickly. So I'm going to type in y equals x, let's go plus 2 cubed. And we can see that at the particular 0, this has, what's happening to the 0 is the graph kind of flattens out as it goes to the 0. If I type in y equals x plus 2, just plain old x plus 2, what we see is the graph going straight through at the 0. If I type in y equals x plus 2 to the 7th, okay, there we go, sorry, that took a little longer. You can see that the graph at the 0 is much flatter than it was for y equals x plus 2 cubed. So the big takeaway here is that you have to notice the difference between an order 1, 0, which goes straight through. Doesn't mean it's a straight line, it just means at the 0 it kind of shoots through. It doesn't do this sort of slow down and start up again, this little dipsy doodle as I call it. And then once you get into the higher odd exponents, it starts to flatten out or do this dipsy doodle. I'm not expecting you to know the difference or be able to look at a graph and tell me whether it's an order 3 or an order 5, an order 7, unless you have something to compare it to. Okay, but for sure I'm expecting you to notice the difference between an order 1 exponent or 0 and an order 3. Okay, let's get back to our note. For zeros of even order, what happens is something different. The graph touches, but it doesn't cross the x-axis. So for example, if we had the function, the same function as before, we'd see that this is a 0 of even order, and so at x equals 1, the graph is going to approach x equals 1, it's going to touch x equals 1, but then it's going to turn and go back from where it came. So let's go and look at that. Sorry. So I'm going to just change x plus 2 to squared, oopsie, not to 32, to squared. And we can see, I'm just going to get rid of this for a second so we can just see. So we can see what's happening here at x equals 2. It comes down, x equals negative 2, sorry, it comes down, it touches at x equals negative 2, and then it turns and goes back up. Okay, so you guys are smart. I know you can predict what's going to happen here. If you just think about it. So if we have to the 6th, you can see it just touches. This isn't touching along the x-axis in many points. At many points it's touching at x equals negative 2 still. But what it does is it comes down and it flattens out before it touches the 0. Okay, and if we look at y equals x plus 2 to the 4th, it comes down, the red one, does not flatten out quite as much as y equals x plus 2 to the 6th. So the flatter the, the higher the exponent, the flatter the graph is toward the 0. Okay, that's your rule of thumb. And the rule of thumb then for the odd order would be the flatter the 0 for as you go up in odd numbers for the 0. Okay, it's getting flatter and flatter. Okay, so let's make sure I covered this. The factor has an order. The graph is positive when it's above the x-axis and it's negative when it's below the x-axis. We already talked about that, but that's important because if it crosses from negative to positive, then you know that there is a zero there of odd order. So let's just look quickly at these examples. I've got this graph here. I can see that right here, this is an order 1, 0 because it just goes straight through. It doesn't do a dipsy doodle. It goes straight through. It goes from negative to positive. So it doesn't have to be a straight line, but it has to look like it's going straight through. This one, of course, is an order 2, 0 because it does this little touch and go. Over here at this particular 0, you can see it comes up, it flattens a bit, and then it keeps going through. This is an even 0 here, but it's not an order 1. It can't be because it doesn't go straight through. It does this little slowdown. So you've got an order 3 at least 0. Okay, we are going to make a distinction now between an even degree polynomial, which we know what they are. The highest exponent is an even number if it's in standard form. And an even function, so it's missing the word degree. An even function is a special type of an even degree polynomial, just like the square is a special type of a rectangle. So in standard form, which is something like this, term, 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 separated by plus and minus signs, all we do to verify if it's an even function is check to make sure all of the exponents of all of the terms are even. And if that's the case, then yes, it's an even function. If it's not in standard form, if it's in factored form, we need to use this property here, which is that the function f of x is equal to f of negative x. What does that mean? Go back to your transformations. This means that it's a reflection in the y-axis. So we can say then that if our original function has been reflected in the y-axis and we get our original function back, that means that there was line symmetry in the y-axis. We can check algebraically by replacing negative x where there's an x in the original function and checking to see if those two functions are exactly the same. So that's even functions. An odd degree function is also an odd function an odd function is also an odd degree function if the exponents are all odd in standard form. And this one for factored form is slightly different. We've got a couple of extra minuses in there. The book uses f of negative x equals negative f of x, so let me explain that. If we have a function f of x and we have a minus in front of it, what that means is it's been reflected in the x-axis. If we have the minus there, of course, it's been reflected in the y-axis. So what this is saying is if you reflect it in the x-axis and then you reflect it separately in the y-axis and you get the same function, then you are, this is an odd function, okay? So here's my original f of x. If I reflect it in the y-axis, that's this one. Sorry, it's not, it's this one. This is the reflection in the y-axis. And then I go ahead and I reflect it in the x-axis. I'm going to take this one again, starting with f of x, reflect it in the x-axis. I'm going to get this. Sorry, that's just me and this tablet thing. I'm going to get this, right? I'm going to get the same graph. So I don't like using this notation. I'm going to ask you to use f of x equals negative f of negative x, which is basically just dividing this one by a negative 1, if you will. So then we get negative f of negative x. So why am I asking you to do that? I just like taking the function and doing all of the transformations to it at once so that we check our original to see if we have the original function. We don't have to do it that way. You can use this method, that's fine. So really what this is saying is take my original function and reflect it in the x and the y-axis all at once. So I'm just going to see if I can erase this. Oh dear. Doesn't seem to. Oh, okay. So just double. I need to move a couple things here to get my pen back. Sorry. Okay. So now, if I reflect this in the y-axis first, I get this. Then I reflect this in the x-axis, I get my original graph back. Okay, so that's what I'm doing with that statement algebraically. And we'll do an example. I know you're probably very confused at this point, but we'll do an example, and hopefully it'll all come together for you. Okay, so for the graph of a polynomial function, it says determine the least possible degree and the sign of the leading coefficient. So we know this is an order 2, 0. This is an order 1, 0. So if I were using my zeros rule, I would know that the least possible degree is the number of zeros. And that's equal to 3. So I could also use my rule for checking the turning points or the max mins, and I can see that I have 2 turning points, so I have plus 1 degree, right, is the least possible degree. So I'm going to say n equals 3, and I'm going to say the sign of the leading coefficient, of course, goes from quadrant 2 to quadrant 4, so we know the sign of the leading coefficient is negative. Okay, let's keep going. What are the x-intercepts? So let me just go back and check that and the factors. So the x-intercepts are at negative 3 and positive 2. So if we go back here, I'm going to say x equals negative 3 and positive 2. And the factors then would be x plus 3. Remember to change the sign when you're putting it inside the factor. And this is going to be squared. And we have another one, x minus 2. And that one was order 1. So it is just x minus 2. Now we're going to figure out the intervals where the function is positive and where it's negative. So we did this already, I believe, yesterday. So hopefully you're understanding the idea of negative and positive. So as we go from left to right, is the graph above the x-axis or is it below the x-axis? So, and we're asking ourselves, what are the x values that make the y positive or the y negative? But we're giving the x values. So we always go from left to right. We're starting here at negative infinity, and what we have to keep in mind is it's the zeros that affect the intervals, because at the zeros the graph is neither positive nor negative. It's Switzerland. It's not positive or negative, it's neutral. So we have to consider everything that's happening at all the zeros. You may look at this and say, oh, the graph is always above the x-axis, so from here all the way over to here it's positive. But that's not true, because it hits a 0 and all of a sudden it's neutral. It's not positive. Okay, so let's come up with these intervals then. We're going to start way over at negative infinity, and we're going to the first 0, negative 3. We're putting a round bracket because the graph is not positive at that particular value, right, at the 0. So the graph is positive there. And then we pick up again from that same 0, and this time we're going to go all the way over to our next 0 at 2. And again, it's not positive or negative at the 2. So that graph is positive in that interval as well. And then from 2 all the way up to infinity, round brackets again, we have that the graph is below the x-axis. Okay, now we want to come up with the equation for the function that corresponds to the graph. So I know that I've got f of x equal, equals a, we have a stretch in there, possibly, x plus 3 squared times x minus 2. I'm going to sub in what I know. I know a point. I think it was the point 0.09, I'm hoping. You can sub in any point other than the zeros, but that one was handed to us on a silver platter, I think, so we're just going to go with that. Okay, so 3 squared is 9, 9 times negative 2, negative 18, and I get a is negative a half. So I'm going to put that all together then. F of x equals negative 1/2 x plus 3 squared x minus 2 is the equation. I want you to go ahead, pause the video, and do question 2, please. It's just another little practice for you. Okay, so hopefully you could see that that was a degree 3 polynomial. The leading coefficient, of course, positive. The x-intercepts were at negative 3, negative 2, and positive 1. And the factors of the function then are x plus 3, x plus 2, and I'm just going to put commas for now, x minus 1. These were all order 1. They all went at the 0. They were going straight through. Okay, the intervals where the function was positive, so it was above the x-axis up until you got to, sorry, it was below the x-axis up until you got to negative 3 if you're going left to right. Then from negative 3 to negative 2, it went above, then it went below, and then at the very end, from 1 on to infinity, it was positive or above the x-axis. Okay? Go ahead and sub in a point. There's all our factors. We did the math, of course, and it came out to a equals 1, so we just have the product of all those factors as our equation. Could have used f of x, probably should have here, but y is acceptable. Okay. So now we're going to do a bit of graph sketching. Excuse me. So we're being asked to graph this one. You've got to use all of the stuff that you've learned for all these 3 lessons now. Okay, so let's just summarize, some of the stuff that you would know. You know the degree of the whole polynomial. You're just going to add up those exponents of the factors. So you know the degree is 4. You know the leading coefficient. Be very, very careful with the leading coefficient. If the factor doesn't start with just x, it has to be in the front, the x, it has to be just x here and here. If it does that, then you can be sure that the leading coefficient is the number in front of your factored form. If it's not x, you need to make it x in order to have the leading coefficient as the number in front. So you would have to do some algebra around that in order to get it in that form. The end behavior is because the leading coefficient was negative and because the degree is 4, think parabola, that's positive, so that's quadrant 2 to 1. So we know that this one's quadrant 3 to quadrant 4. We know the zeros are at negative 1 and positive 2. We just took the opposite sign here and here. And the y-intercept occurs, remember, where x equals 0. So algebraically, we can calculate that very simply. 0, 0, so this is 1 squared is 1, negative 2 squared is 4, so 1 times 4 is 4, 4 times negative 2, negative 8. Okay, so you're going to start by, you're going to start by graphing the zeros, so there we go. Negative 1, 2, and negative 8. Now because that's a y-intercept. Because this is, we're going to go back to all the information we have, including the order of the zeros. So we know that this is the end behaviors from quadrant 3 to quadrant 4. So I know I'm coming from negative infinity here. I know that I'm going to end here. I know this is a degree 4, and I know the order of the zeros. So you go back to your equation and you look and you can see that you've got order 2 zeros. So that means that when the graph gets to that 0, it's going to turn. So it's very difficult to draw on this tablet. Apologies if it doesn't look quite right. I'm getting here, I'm turning. I'm getting here, I'm going through. I'm going to keep going a bit because I want this to be symmetrical between these 2 zeros. So, and this is just sort of almost a guessing game sometimes. There we go. Okay, so I would label the zeros and the y-intercept. Okay, so we've done a pretty good job of sketching that one. You go ahead and try sketching the next one, please. Before you start, actually, I'm just gonna mention that this is not an exact science. You can see here, I wasn't sure where to turn. I could have technically gone on a little more. This part's not important. These little peaks, these turns here are not important. This is not a perfect sketch. Okay, so when you get down to this one, hopefully you're going to get that the degree is 3, the leading coefficient is 1, the end behavior is quadrant 3 to quadrant 1 because the degree is odd. You've got the 3 zeros and the y-intercept is -8. So when you go to graph it, when you're coming here from negative infinity, you don't really know how high to go. So it's okay not to go, like it's okay to sort of guess here how high you want to go before you turn to come back to the next 0. And for this one, you're not just going to go through at the 0 because at the y-intercept, because if I'd done that, I would kind of have an odd looking, well actually that doesn't look so bad if I'm coming from there. But over here, it's going to look much sharper than here. So you're trying to kind of keep these, you're trying to keep them as kind of symmetrical as possible. Okay, it's an art, trust me, and you're going to have a whole worksheet to practice doing that on. But for now, just keep that in mind. You don't have to know where this is. If you're dying to know where this turns, you can actually sub in this point, right? You could sub in x equals -3 to this graph, and you could actually find the y value and you could plot it if you really wanted to know. But that's not an expectation that we have for you, that you will do that. Okay, let's keep going. We're almost done. So it says, without graphing, determine if each polynomial function has line symmetry about the y-axis or point symmetry about the origin. So this is another way of asking, is this function even or odd? Even if there's line symmetry, odd if there's point symmetry. So okay, that's another way of asking this question. And if it's in standard form, you just look at the exponents. This has an exponent of 0 if we put in the term. And so we can see easily, very easily, that this is an even function. And I'll just say, because all exponents are even. This rule doesn't work for factored form. You can't just look at the exponents of the factors and say, oh, it's, for instance, an odd function here because all of the factors have odd exponents. This rule only works when it's in standard form. So here comes the hard part. For this next question, we have to actually figure out algebraically whether this is odd or even. So I am going to use our rule, and remember our rule was even was f of x equals f of negative x. Not sure what just happened there. And for odd, it's f of x equals negative f. My goodness, something strange is going on. Of negative x. All right, so f of x equals, very bizarre. My pen is acting very strange. So let me just try write, oh my goodness. Having all kinds of technical difficulties. So for odd, it's f of x equals negative f of negative x. So that's the one we have to use for in this case. And so I'm going to say, is g of x equal to negative g of negative x? That's the question we have to ask. So what we do here is we take the negative of the whole function, and then we replace every x with negative x. So let's figure out what negative g of negative x is. I'm going to take the negative of the whole function. That's just the negative. If you put a negative in front of the whole function, if it's in factored form, then you get the negative of the function. So this negative has been taken care of by this negative. Now we have to replace every x with negative x. So I'm going to put a negative x here where this x was positive. And if I do that, I have to change that to a positive x. So this was negative x, so a negative negative becomes a positive. I've got also here 2 times negative x plus 3, and then negative x minus 2. Okay, so we've got, if I just clean this up a bit, x, don't need positive in front, and then minus 2x plus 3, and minus x minus 2. When I clean it up again, I'm going to factor out all of the negatives. So I'm going to factor this negative out. It's going to become negative here. So this is 2x minus 3 when I divide both terms by negative 1. This becomes x plus 2. And this becomes positive because I factored that negative out, and a negative times a negative in front is a positive. So I end up with x times 2x minus 3 times x plus 2. Okay, and I'm going to ask myself, is this the same as my original function? I'm going to check. I mean, you can do a visual check and you can see it's not the exact same function, but I'm just going to check the zeros. Okay, so if I checked the zeros here, the zeros here are x equals negative 2. The zeros here are x equals 3/2, and the 0 here is x equals 0. If I look at the zeros of the original, I've got x equals 0, I've got x equals negative 3/2, and I've got x equals 2. Because my zeros are different, I can't possibly have the same function. So, 0, I'll just say zeros, not the same. So, g of x is not equal to negative g of negative x, and we can say therefore there is no point symmetry. Of course, we know there's no line symmetry because this is an odd degree function. There is no point symmetry about the origin. Okay, that's it, that's all. So right now you should be doing your consolidate, and then what I would like you to do is to do the 1.3 graphing using technology worksheet, then do the 1.3 graphing using your hand non-technology method, and then I'd like you to do your homework for 1.3. Thanks a lot.